So here's the title: Frost heave, fluids at grain boundaries and peculiar ice formations. So this is it's kind of a topic that that I've been reading a lot about, because I'm working on this force of crystallization issue that a lot of you have heard me talk about before. And then you stumble upon this ice research a lot. So since it's something that I find interesting, I wanted to share it with you, basically. So it's not really it's not my work. It's just other people's work that I would like to share. And the reason why I put down this part of the title, fluids at grain boundaries, is that most people, or people at PGP, don't usually work on ice, but we work on other melt solid systems that are generally not so easily accessible as ice. So phase transformations take place at higher temperatures and higher pressures, and they take a long time. But some of the general thermodynamics that I will be talking about applies to any material, basically. So I just want you to keep that in mind, that I'm going to be talking about ice and about things that we observe in real time around us. But it could also apply to things that happen deep down in the earth as things solidify. So I took some pictures outside my house this morning, just to show that this is just the right time to be talking about these things. So I don't know how everyone else's houses look like this morning, but you see that there had been some phase transformations going on during the night or the morning, and we're starting to get some frosts appearing. And the issues I'll talk about takes place around the melting point of water, usually. So just the outline, I'll show you the motivation, why this is interesting, I think. And then I'm going to be talking a bit about some experiments that were done about 90 years ago by a geologist called Stephen Tabor, who did some great experiments on these kinds of things. And then I'll move forward to more recent research and try to explain the experiments and the observations in terms of interfacial liquid films and thermodynamics. And then I'm going to just show you some examples. So just to start, I'll start with this just to show you that it's not my work. And I'd like to tell you whose people's work I'm going to be talking about. So there's Stephen Tabor, who has these two classical papers describing his experiments on frost heave. And then I'm going to use some of the work by these guys, John Wettlaufer, Rempel, who have been working on the theory of premelting, and use that to explain frost heave. And then, as I was surfing the web for pictures on frost heave, and I came across this fantastic website by Professor Emeritus in Geology, James Carter, who has compiled these web pages of fascinating ice formations that he finds in his garden and other people's gardens and on walks. And I'd like to just show you some of them and discuss them in this context. So, motivation. Every year, and especially last year, I don't know if it was especially much last year, but I guess it was because they had just finished some very big highway projects in Norway, and then we had a cold winter, and after the winter the roads looked like this. So it said, did not dig deep enough when they built the highway. If you don't, when you build a highway, you have to dig deep enough, and fill in coarse material to avoid frost heave. And that's in the books, but apparently it wasn't done well enough, and they built these short spans of incredibly expensive highway, and now they look like this after one winter. And to repair it, they have to do them again. They have to dig them up, and they have to do everything again. So the Norwegian Automobile Society says their lives will get lost. I'm not going to show this video, but they were interviewing the guy in the Automobile Society as they were driving along this bumpy road, and they had a big semi-truck in front of them going, saying this is not good. And this politician from Senterpartiet, she had enough, so she decided to go into this hole just to show how bad it was. So this is also created by frost. If you get a large buildup of frost underneath the roads, and then the ice melts, then you'll have redistribution of masses basically, and you have space left where there was ice, and then you can get holes and you can get cracks in the roads when cars drive on them. And then there's been a lot of discussion about how the people in charge of building roads don't know enough about heave, frost heave. They're trying to fix it by using this geo radar to look at where frost heave takes place. I don't really know what they do with it. It was just in the newspaper. I was getting curious about this since I was reading about frost heave from the crystal growth perspective, and then I was reading all this news, and I was wondering who did the research in Norway, who were the experts, but I couldn't find really very much on it. So it also can affect buildings. So here's the oldest state church in Norway is in danger because the soils under it are moving. So it's both frost heave during the winter, that some parts of the surface get lifted up and shift the building, and also you have the problem that when it melts, the soil kind of rearranges and you get things sinking in. So here's the one research post that I found on this last winter, forskning.no. So this is the place where research is shown in Norway. There were a couple of guys from Bioforsk in Ås, so they deal with agriculture research mainly. They had picked up this issue of frost heave, and then they had seen a paper from some Canadian study showing that salts can enhance frost heave, and so they said maybe all this salting we do on the roads can affect the frost heave. I think the bio people are also interested in salts because it kills the trees along the road, so maybe that was why these people picked it up. But here, so this is another picture of a bumpy road, and then the typical explanation that you get for frost heave. So frost heave, I didn't really, no one stopped me, but I didn't really define it, did I? So it's what happens when you have freezing water under the surface and then it lifts up the surface. And if it doesn't lift up everything by the same amount, then it can create damage. So the typical explanation is that as water enters the subsurface and it freezes, it expands because ice takes up 9% more volume than liquid water, and so it expands and you get damage. And this is something that we have experienced. Maybe if we lived in cold countries, we might have had burst pipes because of ice formation during the winter. Yes. Yeah, this is what I'll be coming to. Yes. So if you have something confined, if you put a bottle of liquid in the freezer, and there's a cap on it, and it's made of glass, then it will burst if there wasn't enough air in it, because it's confined. The water or the pressure can't escape, and it bursts. But what was recognized by some people among this guy Stephen Tabor in the early 1900s was that sometimes the amount of lifting of the ground was substantially more than 9% of the depth of freezing. So imagine that's 1 foot. That's what's in these papers. Or 10 feet.
You don't have to apologize.
Imagine you have 10 feet of the ground freezing, and then you have an uplift of 3 feet. That could be observed. That's 30%. And then water expands by 9%. So there's some extra stuff there. It doesn't really just fit with this expansion. So that brings me to Stephen Tabor, who did some. I first read his papers on the force of crystallization on different kinds of salts, because he did great experiments on that. But he also did some great experiments on ice. So he was a graduate from Stanford University in 1906, and then he went and did fieldwork. And then he came to the University of Virginia to get his PhD, and then the following year he became a professor in geology as a one-man department at the University of South Carolina. And then I guess he could run his own show and do what he liked, and he did some great things. So yes, this is I don't know. I got this from the website of his university. So I guess this is how long he's served. Yeah, I was wondering about that too. But I tried searching for Stephen Tabor, and this is the only thing I got for Stephen Tabor II, because this is Stephen Tabor II. I don't know who the first was, but the third was apparently very important bee researcher. I don't really remember the word. It has a name. So there's lots of articles about Stephen Tabor III and bees. So, but his father was a geologist. So he became interested in this force of crystallization and frost heave. I guess in maybe 1914, when he started doing some experiments on cold nights. And on cold nights, he did lots of experiments using different materials and different water saturations and all that. And the thing he found out was that water needed to be in contact with some, you could say capillary contact with water from one side. And I'll come back to that. There were some conditions that he found were important for frost heave, but it was difficult to do systematic studies because he had to do them outside, and he was dependent on the weather and so on. So due to lack of facilities, he laid the investigation aside temporarily, and then in March 1927, so he had other things to do for 12 years, but then in March 1927, he had a suitable low-temperature apparatus placed at his disposal by Mr. E.W. Allen, the district manager of the Frigidaire Corporation. This is from his article. And he began a systematic investigation into the mechanics of frost heaving. So this refrigerating apparatus that he got at his disposal was, it had some kind of cooling coils. And he wanted to simulate freezing of soils from above. So he would take these cylinders and fill them with clay, and then have them sealed on the side with wax, and then put them in a container of sand, and have that insulated, and then he would have this cooled air on top, so that he would get freezing from the top down. So this is a nice drawing of one of his experiments. So he would have these cylinders that are sealed on the side, and then they were perforated at the bottom, and then they were in contact with wet sand, and there was and the pressure of water, or the level of water, was maintained through contact with a bigger reservoir of water outside. And then he could freeze the cylinders and look at the effect. So here's one experiment, and I'll just show you the kind of general result first. So the general result is that you get these ice lenses growing horizontally. And so he recorded the depth of freezing, so that's how far down there was any ice present. So it's basically how far down the 0 degree isotherm moved. So he recorded how far down it rose in centimeters, and then he recorded how much it was lifted up, and then he wrote down the ratio of uplift to freezing, which would then be 0.09 if it was just water expanding. So this was around 0.4 in this case. And then he experimented with different loads on top just to simulate this heaving process. So in this experiment, he had one cylinder with wood on top, with a small load, 2 grams per square centimeter. And then in the next one, he had wood and then iron on top. And then the next one, he had just iron. So these two would have similar load on them. And these two would have similar temperature conditions because wood is insulating, and iron is very thermally conducting. So this would have a higher temperature on the surface. And then this is the result. So you see this guy here that had the iron weight on it, lifted up more than this guy who just had wood on it. So he had more to lift, but it was lifted up more. So that suggests that it has something to do with the temperature. Now these two that had similar temperature on top, there was more lifting in this case where there was less weight. So the process, since this is not just water expansion, there's more water in this column now than it was when it started freezing. Because it doesn't match basically with the expansion. So that means that the only place the water could have come from is the bottom. So it means that as this was freezing, it was pulling water in from this wet sand underneath. And that's related to the temperature gradient. And then he was provided by this sample from Lang at the Minnesota Department of Highways, and he put this in his paper just to show the similarity with what happens in the field. So this is clay containing ice layers from under a badly heaved street in St. Peter, Minnesota, and it has the same kind of ice lenses forming. So it's got to have been the same kind of process of water being drawn from underneath and forming lenses beneath the road. And then he did lots of experiments. It's a very thick paper, and it has lots of figures in it. So I'll just show you some of them. For instance, in this case, he didn't put any lateral confinement on the cylinder. He just placed it in viscous oil, and it had a spring on it to confine it. So it still tried to grow upwards, but then it yielded, and it buckled or whatever outwards. So you see still the remnants of these ice lenses, but it's yielded in this direction. And that means because one of the prevailing notions of frost heave had been, in addition to this expansion, to say that it would expand upwards because that's where you had the least resistance. But in this case, you have the most resistance in the upward direction. You still have these lenses forming and growth mainly upwards, and so that's then related to the temperature gradient, not where you have the most resistance to growth. And then he looked into the effect of particle size, because that's also something that had been noted, that the particle size of a soil or whatever material you have under a road is very important for whether you get frost heave or not. So he made, I like these experiments where he had cylinders with different particle size, and he has a whole long story about how he filled them and compacted them and made sure everything was uniform and the water went all the way up and before he started freezing. So here is sand, and this sand is just completely frozen, but you don't see any lenses forming except maybe at the top. And this clay, you see these really thick lenses, this black stuff, this is all ice that's been growing. And in the end the cylinder broke at the bottom, and then this clay was pushed out and it pushed away some of the sand to go underneath here. And in this case it just bent when he took it off. So you had all these lenses forming in the part where there's small particles, and where there's big particles and nothing happened. And another really cool thing that he found, I think, was when he had the clay cylinders and he sealed them at the bottom. So they were completely filled with water, and then they didn't have access to water from the bottom. And then he started freezing them from the top. Then, as water was being drawn to the top for freezing, it dried out the clay at the bottom, and it created these tensile cracks going in this direction. So from the bottom it looks like this. This is the columnar structure. And then as it kept freezing, you got subdivisions in this direction because of this ice lenses forming in each column. So I thought that was pretty cool. So what he concluded from his papers was that there's some mechanism that draws water from below and up to the freezing site. So he said that this must show that there's some film of liquid water between the ice and the matrix. And when the ice is below zero, it keeps freezing, and as it draws then water from this liquid film into the ice, so making the liquid film become thinner, then since this liquid film doesn't want to break, essentially, instead it just draws up more water from below to maintain the liquid film. And then he discussed that maybe the ultimate limit for frost heave would be whether you could actually break this liquid film, and that could maybe be related to boiling in some way, because it's, you have water at just ambient pressure below, and then you have to draw it up. It means you have to put a lower pressure above. It's like you do in trees. You have atmospheric pressure water in the soil, and then you have to lift it upwards. And then he calculated that in his experiments, it would be some of these pressures would be equal to lifting up water to a height of 15 meters. So to do that, you need very high negative pressures, and maybe then at some point you could the negative pressure would be so negative that you would start boiling the water, and then you would break this liquid film, and that would stop frost heaving. That was his hypothesis. So some remarks that he put in his paper said, for those whose conception of frost heaving have been derived from freezing experiments with closed systems, the results obtained in this investigation seem paradoxical. Heaving in clay is greater than on sand, although not all of the water freezes in clays, but practically all of the water freezes in sand. So more of the original water there freezes in sand, but the heaving is more in clays. And then he talks about this tensile stress in the water. and that maybe the boiling point of a liquid seems to be more important than the freezing point in determining the pressure developed by freezing in open systems. And then while water expands in freezing, the freezing of saturated place may be accompanied by the formation of shrinkage cracks due to this withdrawal of water to build ice layers. And then this that I said that the direction of heaving is not related to where we have the most resistance, but it's related to the temperature gradient. So then we take a step into modern days, and then we can try to explain some of his observations. But yeah, I spent quite a lot of time on this, and then I'll spend a short time on the thermodynamics, which is fine for a Friday, I think. So when you're below the freezing temperature of something, you can still have a stable liquid. This could be due to curvature effects, it could be due to dissolved impurities, or it could be due to surface forces, and that's what I'm going to explain. So surface forces seems to be what's important in this case. And as we're talking about a solid melt system, this goes under the term pre-melting. So it's something that melts before everything else melts. So surface melting, or melting below the melting temperature. So there's two components that we have to put into this. The fourth component is the disjoining pressure, and Paul has talked about disjoining pressures in a wine seminar earlier, and I'll do it and I've talked about it before too, so we'll do it again. Imagine that you have a solid and then there's a liquid film on it with a certain thickness, and it could be then separated from either its own vapor or the same solid with a different orientation, making it a grain boundary, or some wall of something that doesn't dissolve in this liquid, so inert in a way. Then the interfacial energy in the system we can call I, and it's a function of the thickness of the film. We can describe it by this relation. So there's the delta gamma, and gamma refers to surface energy. And there's some function of the height, and this is the dry surface energy. So if we say that, and then this delta is the difference between the two wet surface energies and the dry surface energy. If H is very large, so the film is very thick, we just have 3 bulk phases, and then the only thing you have is this interfacial energy and this interfacial energy. And then as you shrink it, you have to approach this value. So it means that as this is 0, then this is 0, and you're left with this energy. So that was quick enough that no one understood. And then I can just tell you that for pre-melting to occur, so for a melt to be stable in this situation, then the energies of the two liquid-solid interfaces has to be smaller than the energy of a solid interface. It means that it costs more to have a solid-solid interface than it does to have a solid to have 2 liquid interfaces. So even though you're below the melting temperature and you would like to freeze everything, it costs so much to make this solid-solid interface that you would rather just refrain from freezing that last portion. And then, since the energy increases as you make this separation thinner, this amounts to moving against the force, and it gives you a pressure. And that means, so that's the destroying pressure, and it means that in this situation, if you have a melt and it's stable, then it has to mean that the pressure that the solid feels is larger than the pressure in the liquid, because there's some forces between the 2 solid surfaces acting on them. So that was that. And then chemical equilibrium. We want the chemical potential of the solid to be equal to the chemical potential of the liquid. We know that at some reference pressure and temperature, the 2 chemical potentials will be equal, and then we just do an expansion around this point. so you move in the direction of pressure, the slope in that direction, and the direction of temperature, and you do the slope in that direction. And then this is by thermodynamics. This is just the volume, and then this is just the entropy. And then you put these two equal, because you're at equilibrium, and you get this relation. And this term here is the latent heat of melting. So that's just the heat of phase transformation. So it means that this when these pressures are different, we can be away from the melting temperature and still have a stable liquid if this is the case. So the liquid pressure is different from the reference pressure, and the solid pressure is different from the reference pressure by this amount. So let's look a bit more at this equation. Let's assume that we're connected to some reservoir which is just at the melting point, and it has this reference pressure and reference temperature. And then if we start cooling it in one place, and we don't put any stress on the solid. So the solid is at pressure Pm, then the liquid pressure where we're cooling needs to be below the pressure of the reservoir in order for all of this to apply. And that means that if you start cooling it in one place, then you make the liquid pressure lower, and then you have movement of liquid, and that's just what happens when you make this ice lenses. And then the pressure in the solid will build up, so allowing the pressure in the liquid to increase up to some point where the liquid pressure is equal to the pressure in the reservoir. And that gives you the maximum frost heave pressure that you can attain, and that's equivalent to this maximum crystallization pressure that I've talked about before, at least. So if you have pure water, this could kind of tell you everything. If you know this equation, it tells you then you have one condition for the difference in solid pressure and liquid pressure, which is determined by the temperature. And then you have another condition, which is determined by the film thickness. So at any temperature, you have an equilibrium film thickness. And so when water is transported, or liquid is transported to the regions where you have lower pressure, then the film becomes thicker, and then to maintain equilibrium, it has to solidify. So it means that you keep growing, and then that makes it kind of a dynamic frost heave situation. So that's kind of two levels of complexity, because one is what do ions do, and how do the chemical potentials behave and everything. But then the other thing is, why do we have frost heave in the first place? Is it because you have water and it expands when it freezes like you do in a bottle? Which is what it says always in the news when there's something about frost heave? Or is it because you draw up water from below and that's what happens? That's kind of the important thing. Yes, that was that with the equation. Oh, I'll put up some more equations so you can argue a bit more, but then I just wanted to kind of briefly tell you how this applies. So again, bumpy roads, and then some of these very cool pictures from Jim Carter's website on ice formations that I'll show you. And then, but then the one theoretical thing I wanted to put in, which I don't know if you will agree with, but that's now that we have these pressures and things worked out, then we can look at what happens if you have a particle embedded in ice, and then you have a thermal gradient. So this could be a particle sitting in permafrost somewhere, a soil particle in permafrost, and it's warming from the top. So it's colder down here. That means you have a higher disjoining pressure down here, lower disjoining pressure up here, and then you have a higher liquid pressure up here, and a lower liquid pressure down here. And let's just say there's no salt. So this is just pure distilled water in this permafrost for some reason. And then you can look at what forces you have. So if you want to know the forces due to this disjoining pressure, you just move around on the particle and you integrate the disjoining pressure on the surface. And then now we have moved to mass. So this is the latent heat per mass. And then so the force then depends on the mass of the particle, or actually of the ice that is displaced, and you get this kind of buoyancy thing where you have the mass, and then you have a term which is due to the temperature gradient and the latent heat, which gives you a force. And then if then we have some flow around it, and it's viscous flow, so we have some dissipation, and that gives you also a force. And if the particle is spherical, we can approximate what this force would be. So that would depend on the particle velocity. Just say that this particle is going to move with some velocity. It's going to depend on the size of the particle, and then h is the thickness of the liquid fold right there, as it's given by equilibrium thermodynamics. And then of course you have the force of gravity. So that takes in the difference in densities between the ice and the particle, and then you can calculate what the velocity of this particle would be. So that would tell you that if you have a steep thermal gradient, your particle would move faster. If you have a small particle, it would move faster than a big particle, for instance. And kind of one cool application of that is that, and I don't really know how true it is, but imagine you're drilling in a glacier for pollen samples, for instance, or just for any kind of fossil record of particles that have been there. And then there's been, due to the thermal gradient, these particles will have moved just a little bit, depending on their size also, so they will have mixed just a bit. And if this is going on for long enough, then it might just disturb your signature, or your signal significantly when you take out these particles and sample them. But then also imagine that you have some freezing front moving with some velocity, and then you have this particle pushing. You can imagine that if these particles would move faster than the freezing front, they would be pushed out of the ice, and then just be pushed in front of the ice. And if they're larger, then they would be embedded in the ice as it moves. And then we can come to velocity, and then just do the same kind of argument, but it becomes more complicated because of the geometry. But you can then also get out this thermal force on the cross-sectional area of the lower boundary of the ice lens, due to the flow and everything. So this is this experiment from Tabor. So it's just coming back to the fact that you have this lens, and you have a force between the soil particles and the ice at that position, and then the ice is moving up, or the ice is pushing the soil particles down, but it makes everything above move upwards. But the other thing that I wanted to just show that is that if you do these equations, and I won't do it because it's kind of complicated geometry, but you also get some constraint on how small the pore throats need to be. So that's kind of a measure of how small the particles need to be in order to lift a certain overburden. So this is the overburden pressure. So and it has to do with how far ice propagates down from an ice lens, and at what temperature you get the ice lens forming. So the more you want to lift up, the finer grain material you need to have, basically, and that's kind of be shown by this theory also. So this simple theory that has there's a lot of things missing from it, but it can still explain some of the basic findings, and also how it's related to freezing rate. And then I just wanted to show you a few nice examples of things related to this pre-melting and water in porous media. So needle ice, it can form on soils or just below a layer of soil, for instance, and then you have these needles and you have some grains on top and you can walk on it and it crunches. And this is also because of the porous material underneath. The pores are small enough that you have, and because of this surface effect, you have liquid layer being drawn up to the freezing site, which in this case is just on top here, and then to each of the freezing sites you have supply of water at the base of a needle, and then you grow this beautiful needle. It pushes the needle up, yeah. So it's frost heave on a very small scale. And then there's this Jim Carter. He noticed these things growing from plants in his garden, and plants are very great examples of porous media transporting water. And then apparently, if they had a small slit in them or something, then they would have ice growing. Just all this, it's lots of ice. So all of this water wasn't in the stem to begin with. So this ice, so the stem has been containing water, and then the temperature drops, and then you nucleate ice just on the outside of the porous material. And then water is drawn to where it freezes, and it's just being pushed out, and it's drawing water up from the soil. And I actually found, and we can see if this works. Someone made a video of it, which I thought was pretty cool. So you can see. So they made this video during the night, so then you see. So this is one night, and this must have been freezing pretty quick, and then it melts. That's not so interesting. So you see, it's where the bark is gone, so the biggest damage, and the pores are open right there. And then another example is this is called ice in German. I found out it's hair ice, and apparently, or this guy claims that it's only found in some specific places like the eastern Canada and some places in Europe, which is kind of hard to understand. But it's growing from dead wood, and it's much more thin fibers than this flowers that you saw before. But it's the same kind of phenomenon. Really cool. And then he has, and these things I don't know how they form actually, but they form from pipes. So these are pipes, and I don't know if they're porous inside. Maybe they are porous because they've been rusting or something on the inside. But anyway, they grow these really cool things out of a hole. So he has pictures from Russia, and then he made some himself in his garden from experimenting with different pipes. So that is it. This was one that he grew from. He found out that if it had just this kind of hole, and it would make it. And here's another example of a row that's been broken due to frost heave, and that's it. Thank you very much for listening.